Hello everyone, I'm Aditya R. Hirmat. Me along with my teammates Aditya Maheshwari and Amrita Varshini M have built a project. The project is titled as Enhancing Parkinson's Disease Management through a Machine Learning Based System for Early Detection and Stage-Wise Assessment. This project was undertaken under the guidance of Dr. Anil Kumardi, Professor, Department of Electronics and Communication. The introduction. Parkinson's disease is a chronic progressive neurodegenerative disorder that affects movement, balance, coordination, and other daily life activities of the affected person. It results from the loss of dopamine producing neurons in the substantia nigra, which is present in the midbrain, disrupting both motor and non-motor controls. Dopamine is a messenger molecule in the brain that allows nerve cells to communicate with each other. It is proven critical to the central nervous system functions such as movement, pleasure, attention, mood, and motivation. Now, we'll talk about the motor symptoms. Tremors, one of the most recognizable signs, often starting in the hand, especially at rest. Bradykinesia, difficulty in initiating and completing movements caused due to the slowness. Muscle rigidity, stiffness and resistance in muscles leading to discomfort and reduced flexibility. Postural instability, difficulty in maintaining balance, increasing the risk to fall. And the last one is gait abnormalities, shuffling walk, reduced arm swing, and difficulty in initiating turns. Some of the non-motor symptoms are as follows: cognitive decline, problems with memory, problem-solving ability, and attention. Mood disorders due to depression, anxiety, and apathy. Sleep disturbances caused due to insomnia, excessive daytime sleepiness. Autonomic dysfunctions, issues such as constipation, urinary problems, and low BP. Speech and swallowing problems while initiating talking. As of now, there is no definitive cure for Parkinson's disease, but early intervention of this disease can significantly slow down its progression and improve the quality of life of the affected person. Some of the medications which are recommended involve levodopa, carbidopa, MOAB inhibitors, which mimic the activity of dopamine in the brain. A few surgical treatments such as deep brain simulations, gene therapy, and stem therapy are also recommended. The lifestyle adjustments such as regular exercise, a healthy diet, and stress management is advised by the doctor. So, this is the problem statement of a project. To address the lack of accurate, non-invasive, friendly, and scalable methods for early detection of Parkinson's disease, present conventional diagnosis methods often rely on subjective clinical assessments, leading to misdiagnosis or delays. By integrating real-time data from voice, spiral and wave hand drawing, ECG pattern, gait shuffle, and SpO2 sensor data, the aim is to develop an efficient system for early diagnosis and timely intervention of Parkinson's disease. These are the objectives of our project. The project is titled to be accurate, non-invasive, and low-cost system. It also integrates multimodal parameter analysis to detect PD, enhance the diagnosis based on machine learning system, real-time data extraction using sensor hardware, user-friendly software portal design for patients and caregivers, interactive and engaging gamified data extraction, generate insights and automate reporting process which help the doctors, patient assistant portal for caregivers. The parameters which were considered for this project are as follows. The first one is voice analysis, which analyzes the vocal tremors and speech irregularities. The next one is spiral hand drawing, which evaluates the drawing irregularities and statutory hand movement through spiral sketches to identify motor control issues. The next one is wave hand drawing, assess precision and hand movement in two axes by analyzing the movement of the wrist and the elbow to detect slowness in movement. The fourth one is ECG analysis, which monitors the cardiac rhythm abnormalities linked to the autonomic dysfunction in PD. The fifth one is heart rate and SpO2 analysis. Rag fluctuations in heart rate and body oxygen saturation levels help us to identify the autonomic nervous system impairments. And the last one is the gait analysis, which help us detect shuffling, reduced stride length, and asymmetry in walking patterns of the patient. Now we come to the machine learning aspect. The following health parameters were trained. The first one is the voice analysis. The XGBoost machine learning model was taken to train this particular parameter. XGBoost is a gradient boosting algorithm which is based on the principle of additive stage-wise algorithm. It consists of multiple decision tree classifier algorithm which are aggregated together. The next one is the spiral and wave hand drawing analysis, for which we used a CAD boosting algorithm, which is based on integrating different decision tree classifiers, and then it classifies based on the symmetry of the given image. The next one is the ECG analysis. We use the gradient boosting algorithm model, which is a simple stage-wise classifier which analyzes the weaker section of the data and integrates it with the higher section of the data. And the last one is the gate analysis, for which we use the ADA boost classifier. Here, the weaker section of the data is trained according to the stronger section of the data based on stage-wise assessment. Now we come to the vocal features which are extracted from the patient. A few involve fundamental frequency, maximum and minimum fundamental frequencies, jitters, shimmers, noise to harmonic ratios, harmonic to noise ratios, pitch period entropy. These features were extracted using the Python libraries of Librosa, Pratt Parcel, PyAudio Analysis, and Python speech features. Once the input audio file is given by the person, we extract the amplitude envelope as follows, which helps us analyze the variation in their pitch and the jitters in their vocal file. The following machine learning models were trained, such as KNN, SVM, logistic regressor, random forest classifier, Naive Bayes, decision tree, LDA, and XGBoost, among which XGBoost came out as the most accurate model with an accuracy of 90% for voice analysis. Now we move on to the spiral hand drawing analysis. The person here is asked to draw a spiral drawing as shown in the image. Based on the closeness of the drawing, the shakiness in the drawing, and the tremors which are identified, the image is classified either to be healthy or Parkinson as shown in the image here. Similarly, we analyze the wave hand drawings. The person has to draw a wave which involves moving their elbow and their wrist. So we analyze the hand movement in two axes in the wave drawing analysis. Earlier, we had a Raspberry Pi system involving a Raspberry Pi camera which used to detect the spiral and wave hand drawings and classify accordingly. But now, to make the system more cost efficient and simple to use, we have integrated the system where the patient can directly draw the drawing and then input the image through a mobile or a tablet. Once the input image is given, the image undergoes pixelation, where each image is classified into a 250 x 250 formatted pixels to extract features from each pixel and draw the analysis. For both spiral and wave hand drawing analysis, we got the CAD boost algorithm as the best model with an accuracy of 87.5 and 89.5% respectively. As I mentioned, CAD boosting classifier is a type of gradient boosting algorithm where multiple decision tree classifiers are involved, and the images which are inputted are classified based on the symmetrical algorithms. Now we move on to the ECG data extracted. We extract data with the help of this particular sensor, which is the ADA8232 sensor. We extract data such as QRS duration, PR interval, QT interval, the depth of T and P interval, QRS range, QRST interval, heart rate, RR interval, and heart rate virality. The AD8232 ECG sensor and Arduino Uno was used to extract the particular ECG data. This consists of three electrodes which has to be placed on the chest of the affected patient. The Arduino Uno is then connected to the Arduino IDE and it is ran in a local environment. Then we connected it to the Python module which helps us to extract the necessary information. We also have another sensor which is Max 30100 sensor, which helps us to analyze the heart rate and SpO2 level of the patient. Once these sensors are run in the local environment, and then the following information is extracted using the designed Python file, we get the following graphs. The variation of ECG pattern is extracted from the patient to detect the necessary features. The variation of heart rate and SpO2 levels are also extracted using the same. For ECG analysis, we got the gradient boosting algorithm as the best model with an accuracy of around 96.1. In this case, we used less data sets as more data sets of affected Parkinson patients weren't available. Now, we move on to the gate data extracted. Using the MAC IMU 6050 sensor, we can extract the accelerometer and gyroscopic data in 3 axes each. As I mentioned, this is the MPU 6050 IMU sensor. We are using two such sensors, which is placed either on the chest and the back of the patient or on both the hands of the patient. This will help us analyze the stride length. When the person is asked to walk on a straight line, we'll understand if their movement is aligned according to the straight line. We'll analyze the symmetry in their movement, the slowness in initiating a turn, and the stride length, which includes the gait shuffles. Once we run this sensor in the local IDE environment and then extract the necessary features using the Python script, the variation of gyroscopic and accelerometer data are shown as follows from the patient. For the gait analysis, we got the ADA boost classifier as the best algorithm with an accuracy of around 85.71%. The ADA boost algorithm is a type of gradient boosting algorithm which is employed when the data is really complex. It classifies the given data based on the weaker section of the algorithm and then matches it accordingly to the stronger section of the algorithm. Now, we'll move on to the software requirements of a project. We used VS Code as our environment, Arduino IDE as our biosensors and Arduino environment. We also used Python as our main language or the script. Earlier, we used a Raspbian when we were using the Raspberry Pi and Pi camera module. Streamlit is the main module which helped us to deploy this particular software. It's a tool which helps us deploy Python-based scripts. Earlier, our initial plan was to do this on a cloud environment, so we used the Google Colab. But then, when the challenge we faced was with the hardware integration, using a cloud environment would result in latency, which wouldn't give efficient data and efficient analysis. That is why we moved into a local environment. React.js is used for the front-end development. MongoDB is our database. Flask is our API. And Pygame helps us to design the games which help us with data extraction. Now, I'll discuss about the system architecture of our project. It consists of two hardware divisions. One is the Raspberry Pi module. Another one is ESP32 or Arduino based module. The Arduino based module will have SpO2 sensor, MPU sensor and ECG sensor, whereas the Raspberry Pi module consists of the microphone, Pi camera, the keyboard and the display. Instead of the Raspberry Pi module, we have moved onto a local environment such as a mobile or a laptop to simplify the process. Now, the software portal is hosted on Streamlit, which helps us to input the data and analyze the given input data. Machine learning models were earlier hosted on Google Colab, but now they are moved onto a local environment such as VS Code. The wellness activities, which include typing game, breathing game, and the mouse stability game, are hosted on Pygame. The database is stored in MongoDB, which are moved through Flask APIs. This is the implementation phase of our project. The input data, which is our data sets, were taken in. The data filtration and pre-processing was done. The data was split according to test and training data in a ratio of 70 is to 30. The models were trained. The trained models were then examined using the testing data. Based on the evaluation parameters of accuracy, precision, log loss, F1 score, and confusion matrix, the best model was selected. The selected module was then imported using the joblib file, also known as the pickle file, and the following ML models for each parameter was extracted. This extracted joblib file acted as the backend of our patient assistance portal. Once the patient comes into the portal, they have to save their information such as name, age, weight, height, and if they had any other diseases earlier. Then they select the parameter which they want to analyze based on voice, hand drawing, ECG, gait, and SpO2. Once they select the parameter, they have to do the biomedical sensor setup where they have to connect the Arduino boards to their laptops. Then they have to enable the serial port connection and then run the particular Arduino in the local environment. Then the corresponding Python script is ran and the necessary information is extracted. After the data extraction is completed, the necessary plots and data are saved in the local environment in an Excel format. Then, based on the data extracted, the patient has to give them as an input to the software. Once the input is given, the software analyzes and gives a prediction if the person has Parkinson or if they're free of Parkinson. The results are given on the software portal. The software portal also has a feature where the analysis and reports are saved. This can be further used to share it with the doctor or the caregiver. To facilitate and simplify the process of data extraction, we have designed a few games such as the breathing game, mouse hovering stability game, and a typing racer, which helps us to understand the movement of the person and which also helps us with the data extraction part. As I mentioned earlier, these are the particular portal functions we have: patient information, disease detection, analytics section, report generation section, doctor contact, and games section. To make data extraction interactive and engaging, as I mentioned earlier, we have 3 games. The first one is the typing racer, which monitors the tappy keystroke, stride accuracy, and timing. It also takes a toll on the cognitive ability of the patient to analyze how their hands move based on the word which is displayed on the monitor. The next one is the star connector, which monitors the hovering stability, the cognitive abilities, and persistence, which is a game which is designed which has to be played using a mouse. The third one is the breath follower to improve the cardiac activity enhancing. While the ECG pattern is extracted, the person has to follow the breath bar which is shown on the display when the corresponding ECG sensor is connected to their chest. This improves the cardiac activity and helps us take in clearer data from the ECG sensor. Now, after explaining this, I would like to show the reports generated, the analysis, the machine learning models, and the games which we have designed accordingly. Hello guys, now I'll show about the hardware which is extracted and the games part along with software portal of our project. So I'll start off with the voice data. So I have this sample voice of the Parkinson affected patient. So in this particular audio file, we can notice the irregularities and the tremors, which includes the shakiness in the voice while this particular voice was recorded. This somewhat indicates that the person has Parkinson. Now I'll show the spiral and wave drawings. So as I earlier mentioned that the person will be given a trace image of the spiral. So the person has to rotate their wrist and draw this particular spiral drawing. So this analyzes the statutory movement of the hand. So based on the shakiness and the shakiness and the tremors of the drawing, it is classified if the person has Parkinson or not. So this is the drawing of the affected patient. We can clearly notice that it is irregular and consists of tremors. Same goes with the wave drawing. So in this case, the person will be given a trace image of the wave. The person has to move their wrist as well as their elbow to draw this particular drawing. So here we'll analyze the hand movement and bradykinesia. So based on the irregularity and the shakiness while drawing, it is classified as Parkinson or healthy. So earlier we had a Raspberry Pi system which helped us with inputting these images using a Raspberry Pi camera and the inbuilt microphone, but that was costing us more and it wasn't that cost effective. So we moved on to a simpler approach where the particular drawings can be done on a say plain paper, and then these images can be inputted using a camera from the mobile or a tablet, or by giving it as an input feed directly to the website using the desktop. Now I'll move on to the ECG data analysis. So this is done using the ECG sensor, the AD8232 ECG sensor. So it consists of 3 electrodes which has to be mounted on the chest of the person or on the either hands of the person. So once this is connected, we'll run the local environment to set the Arduino. So we have to select the board, connect the board to the laptop, and then run this particular script to initiate this in the local Arduino IDE environment. Once this is done, we'll move on to the Python script. This particular ECG Python script helps us to extract the necessary ECG data such as the heart rate virality, the QT intervals, the RR interval peak, and more. So once the sensor is connected to the laptop, we'll run this particular Python script when these electrodes are placed onto the chest of the person. This particular script runs for around 2 minutes, where the person has to swiftly breathe for this to analyze and monitor the cardiac pattern of the patient. Once this particular script is ran completely, we'll get the Excel file which is saved onto the local environment, which consists of all the data combined into an array. This consists, as I mentioned, this consists of the R peak time, the P wave time, the T wave time, the PR intervals, the QT intervals, the heart rate virality, the RR intervals, SpO2, temperature, which is being analyzed by Max 30100, which follows the same pattern, and then this is combined into a array format. Once the Python script is ran completely, we'll get the ECG pattern waveform, which is saved onto the local environment. Same goes with the heartbeat SpO2 sensor, which is the Max 30100, and we have the gate sensors. So this also follows the same methodology, where the IMU 6050 has to be connected to the laptop. First, it has to be run in the local Arduino IDE environment using this particular Arduino script. Then, once this is done and the local environment is set up, we'll run this particular Python file. The Python file extracts the accelerometer and gyroscopic data in 3 different axes. Once the data is extracted, we'll get the necessary data in an Excel format. As I mentioned, it consists of accelerometer data in 3 axes and the gyroscopic data with the timestamp. Then once this is complete, we'll get the plot of the MPU sensor. So in this case, the left hand was simulated to be a healthy person, so we don't see much irregularities in the movement. Whereas when we simulated this for a right hand, the plot was simulated to be of an affected person, so we can see more irregularities in their movement. So once the plots are saved accordingly and the necessary Excel files are saved after running the Python scripts, we can move on to the software portal. So this is the overview of the software portal which we have designed. On the home page, it consists of the different health parameter tests that the person can undergo. It consists of a step-by-step guide on how to use it, and it consists of a separate section which gives us information on the doctors that the person can consult. Then we have the page dedicated for patient information. So say I'll input the patient name, I'll save the age, necessary information like height, weight, and contact information, and then save the patient info. Then I'll now show the step-by-step execution of this software portal. So if we move on to the spiral analysis. So as we have deployed this on Streamlit, it takes a little time. So this is the model spiral image which the patient has to trace. So I'll give a spiral file, I'll give a healthy file. So the system has to analyze this. So the machine learning, which is the backend of the software portal, which is integrated using the pickle or joblib file, predicts the image to be healthy. It gives us a toll on the structural similarity and estimated tremor deviation. Now, same is the case with the wave analysis. This is the reference wave image that the patient has to trace. So in this case, say I'll give an affected person. So in this case, the system has predicted it to be affected by Parkinson rightly, and it also gives us an overlay comparison of the reference image and the image drawn by the patient. Now similarly, we'll go on to the voice analysis. I'll give the input affected voice patient's file. So it takes some time to extract the necessary features and then draws the analysis. So this particular software was hosted and deployed on Streamlit, which is a platform which helps us to deploy Python-based scripts, and it is free of cost, so we thought of going to this. So as expected, the voice file was classified as Parkinson with the necessary information of the extracted features saved in a table format. Now I'll go to the ECG analysis. So here the person or the caretaker has to input the Excel file which is saved after the Python script is ran. Then we'll give the images of the ECG waveform and SpO2 and oxygen level waveforms. Then we click on predict. So once the prediction is completed, the patient is classified to be healthy, as this particular ECG sensor data was extracted from me, so it is extracted to be healthy. And then similarly is the case with gait. So we have to input the gait data which is saved in the Excel format. In our case, the left hand data was extracted to be of a healthy person. So I'll do the analysis. Let's see if it predicts rightly. Oh, just a second. Now I'll move on to the right hand. And give the right hand data. Which is rightly predicted as to be a Parkinson. So now I'll input the left hand data. And it is rightly predicted to be healthy. So then we move on to the next one. Yeah. So once all the analysis are done, we move on to the report section where the patient information and the results of each parameter are saved with the drawings and the ECG patterns, wave patterns, and the gait abnormalities. All the graphs are saved accordingly. This can be saved onto a report which can be extracted into a PDF format. This can be passed on to the caregivers or the doctors, which consists of values of each features which are extracted. So this is for voice. This is related to the ECG data with the necessary graphs plotted. This is with respect to gait, and it also consists of a separate section for doctor contact, which can help the patient to give a call to the doctors if the condition is severe. So it also consists of a section for project details, and this is related to the games. So currently we have 3 games in place which helps us with the data extraction: the typing racer, the star connector game, and the follow the breath game. So now I'll show the games. Currently the games aren't really hosted on Streamlit as it has a limitation, but it is ready in the local environment, so I'll show that to you guys. So this is the typing racer game. So the MPU sensors will be mounted onto the hands of the person. So they have to type all the letters which are coming and click on space to save it. The person will be given 5 lives to complete the particular task. So say person misses a particular word or something, or types it wrongly, that won't be saved and the life will be cancelled. So we can set the complexity of this game, the number of letters that has to be shown out and stuff like that. So this will help us to understand the stride, the hand movement activity of the patient, their cognitive abilities, and the way they think, if they're using only their right hand or their left hand, or how they're moving on the keyboard. So this gives us a toll on their mental abilities. So say once I finish the game, the necessary data will be saved. So once the games are done, we'll get the Excel file. So here we'll get an information of the keystroke, the total time taken to finish the game, the typing speed in clicks per second and words per minute, the number of words that were correct, the number of incorrect words, and a total toll on their accuracy of typing, with the number of mistakes, the longest word which was given to them, and the maximum streak. So this information can help us understand their typing style, the mental ability, and their cognitive decline. So the next game which we designed was the star connector. So here the patient has to use a mouse and then connect these particular stars. So this will help us understand how they are thinking, how their hovering stability is. So based on the amount of time they click on a particular star, it will get selected. They have to finish this particular constellation and move on to the next level. So the selection of each star is based on their hovering ability and the time they take, the time taken by them to select a particular star. So each star has a different time, so they have to click multiple times and then select a particular one. So this will help us understand their mental persistence, their ability to finish a particular puzzle or a task given to them, and so on. So this once the game is completed, the necessary information is stored. So this gives us a toll on the total time taken by the patient, the number of stars they have clicked, and the number of levels they have completed. In my case it was 3, the average time taken per star, the click precision, the hovering stability, and their direction sense, and the total hover time. So this was one of the wellness activity. The last one is the breathing game. For this particular game, we have to mount the ECG sensors onto their chest. So while they're following the breathing patterns, it will help us extract the cardiac rhythm more clearly and help us detect the RR interval effectively. So the person has to inhale and follow the blue bar by clicking on the space button. So while this breathing activity is done, the ECG sensor mounted onto their chest will extract the necessary information more clearly. So this game is designed to for 2 minutes. Once the game is completed, we get the necessary information which is stored. So we'll get the knowledge about the expected inhale time, the actual inhale time if the person inhaled for a lesser second. So this will help us detect short breaths and the deviation from the actual inhale time and the inhale time done by the patient. So this will help us understand if there's any connection between Parkinson and the inhale time and the cardiac activities of the patient. So these particular games help us with the ease of data extraction, help us with future research, and help us understand how these particular parameters are seen in the affected patient. So hello guys, now I'll just give an overview of the hardware components which we have used. So we started this project by using the Raspberry Pi 4 module with the Pi 4 camera. So that was our initial plan, as the system was based on the hardware, the hand drawings, which are the spiral and wave hand drawings. It also consisted of an inbuilt microphone module which helps us extract the necessary audio information. But then when we bought in other biomedical sensors like the ECG sensor and the MAX 30100, including the MPU sensor, we faced a little challenge while we were integrating it with the Raspberry interface. So we then moved on to a ESP32 setup. So ESP32 setup was really helpful because it consists of an inbuilt Wi-Fi module which helps us with cloud computing. But then the challenge which we faced was the latency. So the information which was extracted wasn't that accurate because of the latency. And then when we were processing it on a cloud environment such as the Google Colab, it was taking more processing time, and the results which were given out weren't accurate because the input information extracted by these sensors were a little corrupted. So to make the system more accurate, low cost, and a modular kind of a setup, we then moved on to an Arduino interface. So currently we are using 4 Arduino Uno boards, which consists of 3 different sensors. The first one is the AD8232 ECG sensor, which consists of 3 electrodes. These electrodes are placed onto the chest or the arm of the patient. Then this Arduino Uno is connected to the laptop, and the local Arduino IDE environment is ran through. Then, as I showcased earlier, the Python script is ran, and the necessary information such as the heart rate variability, R2R interval, the PT intervals, and all the other heart related necessary information are extracted. So this process takes around 2 minutes, and the breathing pattern of the patient has to be really accurate, enhanced during this period. So we have designed a particular game for this, which I showcased earlier. The next one is the Max 30100 heart rate and body oxygen level SpO2 sensor. So here the person has to place their either the ring finger or their index finger onto the sensor. So the sensor has 2 configurations. Either it can be done using the resistors, or it can be internally connected. So the person has to place their index finger, and the body oxygen levels and the heart rate is analyzed by this particular sensor. Then we move on to the MPU 6050 IMU sensor. These 2 sensors help us extract the necessary accelerometer and gyroscopic data of the patient in 3 different axes of X, Y, and Z when the patient is moving. So it is housed into a box kind of a format. So this is actually intended to be designed, and the data is designed to be extracted when these sensors are placed onto the body of the affected patient. So say one sensor will be placed onto the chest and one will be placed onto the back, and the person will be asked to move on a straight line. So based on the accuracy of how they're following that particular path, the time taken by them to initiate any turns, the symmetry in their walking style, the stride length, and the total time taken by the patient is analyzed by these sensors. So we can analyze their gait shuffles, their bradykinesia, which is slowness in initiating movement, and if there are any irregularities or concerns while they're moving. So currently, to make this more simpler for the patient, we made it to be placed on each one of the hands. So there are 2 tasks. One is to hold it in the hand for a particular period of time, and then map it along a particular direction or a pattern, say a square or a circle. So if they're mapping it accordingly and effectively without any shakiness, so the data will be taken in. As I showed earlier, for the left hand, it was simulated to be a healthy patient. So the patient was mapping it rightly by slowly moving his hand and making a square, while as the right hand part which was simulated consisted of more jitters and shakiness while it was mapping. So this simulated us of a Parkinson affected person. So in a real time scenario, the person will be asked to walk on a straight line, and based on their walking style, the data will be extracted, and then the model will give us the results. So these are the sensors which we are currently using. Our plan in the future is to make a dedicated board for this, where the board consists of all the sensors as I mentioned. Currently, as these sensors are available in the market and are subjected to degradation easily, we are using a modular kind of a setup, say one of the sensors burns out, we can replace it easily. If we are successful in designing a simpler board and making it on a particular embedded system, then it will be more challenging and more efficient to use, is what I can say. So this is an overview of our project. I hope you guys liked it. Thank you.